Can a moon have its own moon? And if so, what would we even call something like that? Plus, do we know of any moons out there that could actually pull this off? A few years back, my research team discovered Kepler 1625b, the first ever candidate for an exomoon. But what made this one so mind-blowing was its sheer size, a Neptune-sized moon orbiting a super-Jupiter mass planet. Even today, we still don't know for sure if it's real because Kepler had a mechanical failure that kept it from checking the star again. Still, just last year, right here in the Cool Worlds lab, we found our second exomoon candidate, Kepler 1708b. Once again, it was wild, a mini Neptune-sized moon, this time circling a Jupiter-sized planet. Even though these still aren't confirmed, they've sparked a ton of debate, and one question I keep getting is, could these moons have moons of their own? Now, since Kepler 1625b is Neptune-sized, it's tempting to compare it to Uranus and Neptune, which both have dozens of moons. So you'd think submoons, let's call them that for now, might be totally possible. But here's the thing. Uranus and Neptune are planets, meaning their history is way different from Kepler 1625b's. So realistically, we probably shouldn't expect to find anything orbiting it, but here's the least controversial take. Yes, a small satellite can orbit a moon, because we've already done it. We've actually been doing it since the 1960s. In March 1966, the Soviet Luna 10 mission became the first of many to successfully orbit the moon, completing over 460 orbits before the mission ended. Now, sure, that was a satellite, but not a natural one, and definitely not one that stuck around forever. Plus, by astronomical standards, those were just tiny objects. So the real question is, how big of a moon could actually stay in orbit around another moon long term? To figure this out, let's back up and ask, even if a moon somehow got its own satellite, let's keep calling them submoons, could those submoons survive for billions of years? Because making a submoon is one thing, keeping it is another. A smaller object orbiting a bigger one can be lost in two main ways. It either gets too close or drifts too far away. If they get too close, the smaller object can get torn apart by tidal forces or just smash straight into the larger one in a dramatic collision. On the flip side, if they drift too far apart, the gravitational pull from other objects in the system can break them up. Now, for a moon orbiting a planet, the main outside force messing with them is the star they both orbit. The maximum distance where the star won't steal the moon away is called the Hill sphere, one of the biggest deals in orbital mechanics. If a moon wanders outside this zone, which technically isn't a perfect sphere, it's gone for good. And honestly, even getting about halfway to that limit is usually enough to lose it. So why do these inner and outer limits matter so much? Because moons don't stay put. Their orbits shift over time. Every single moon in the solar system is slowly changing its orbit bit by bit every day. Nothing lasts forever. Take our own moon, for example. It's drifting away from Earth at 4 centimeters per year. Why? One word: tides. The moon creates tides on Earth, giving us 2 high tides a day. This happens because the moon's gravity pulls harder on the side of Earth closest to it, stretching the oceans toward it and slightly away on the opposite side, creating 2 bulges. Now, since Earth spins once every 24 hours, way faster than the moon orbits us, these bulges try to race ahead of the moon, but the moon's gravity keeps yanking them back. This tug of war actually slows down Earth's rotation little by little over time. But here's the thing. The Earth-Moon system, just like any other pair of orbiting objects, has to conserve angular momentum. So when the Earth slows down, that energy has to go somewhere else in the system. Think of it like a figure skater stretching their arms out to slow down. The Earth is basically pushing the Moon away, forcing it into a wider and wider orbit. Now, if the Moon were more massive, this whole process would happen even faster because it would create stronger tides on Earth. But if you made the Moon too heavy, it'd spiral outward so quickly that it could escape Earth's hill sphere in just a few billion years, or less, making it an unstable moon. So here's the deal. Technically, you could stick any size moon around any planet and it'd work. For a little while. But if you want something that lasts billions of years, really big moons are risky, because they move away way too fast due to tidal forces. Oh, and just to be clear, this migration isn't always outward. If Earth spun slower than the Moon's orbital period, a lunar month, the Moon would actually slowly fall toward us. And let's just say, Moonfall did not get this right on screen. This whole in and out movement called tidal acceleration is the main reason there's a limit to how big a moon a planet can hold on to. And by extension, it's also why there's a limit to how big a submoon a moon can keep around. Just like a planet has a hill sphere where its gravity beats the stars and lets it hold moons, a moon has its own smaller hill sphere where its gravity beats the planets, meaning it could, in theory, hold submoons. But here's the catch. Just being inside the moon's hill sphere isn't enough. The submoon also has to be small enough to stick around for billions of years. If it's too big, the tides it creates on the moon will kick it out way too fast. Most of this tidal evolution theory was figured out decades ago, especially in a classic 2002 paper by Barnes and O'Brien. So really you can just take their work, swap a few labels and apply it to submoons instead. And that's exactly what Kollmeier and Raymond did back in 2019, right after we announced Kepler 1625b. So let's break down their findings, starting with Saturn as a fascinating test case. In this diagram, they assumed the submoon was pretty small, just 10 kilometers across as a baseline example. On the X and Y axes, they tweaked the properties of the host moon. The X-axis shows how far the moon is from Saturn. The Y-axis adjusts the size of the moon itself. Their results showed that any moons above this solid line could hold on to a 10-kilometer submoon, which seems like great news. And honestly, this makes total sense. The farther out the moon is from Saturn, the bigger its hill sphere, since Saturn's gravity weakens with distance. We can also play with the submoon size. Bump it up to 20 kilometers, and the limit shifts to this dashed line. Shrink it to 5 kilometers and we get this dotted line. So far, this is all pretty broad, but now let's plot Saturn's actual moons onto this graph. Titan, Saturn's largest moon, could theoretically host a submoon, but the real standout? Its underrated sibling Iapetus, which steals the crown as the best submoon host in the solar system. According to this model, Iapetus could hold onto a submoon up to 195 kilometers wide, about the size of Mimas. Looking beyond Saturn, Callisto, around Jupiter and Earth's moon, could also cling to tiny submoons. But neither dethrones Iapetus as the theoretical submoon champ. Now here's the catch. No known submoons orbit Iapetus, Callisto, Titan, or our moon. So does that mean submoons are impossible? Not necessarily. Remember, moons are always shifting their orbits. So here's the deal. It's totally possible these moons started out much closer to their planets, meaning their hill spheres were smaller back then. That'd explain why any submoons they might have had got kicked out early, leaving us with none today. But get this, Kallmeyer and Raymond actually think Iapetus might be hiding clues about a long-lost submoon. See, Iapetus has this weird equatorial ridge that's still a total mystery in planetary science. Back in 2011, scientists proposed a wild idea. Something slammed into Iapetus, creating both a temporary submoon and a debris ring. Over time, the submoon could have drifted outward and escaped, just like we've been talking about, while the debris ring fell inward, possibly forming that ridge. Now, solar system submoons are fun to think about, but things get way more exciting when we look at those giant exomoon candidates like Kepler 1625b. A moon that big could theoretically hold onto a submoon the size of Ceres, a whole dwarf planet's worth of moon. Of course, something that small would still be invisible to our current tech, even with JWST. But if these megamoons are real, there's gotta be more out there, meaning we might someday find the ultimate submoon host. So how crazy could this get? Let's imagine the most extreme case. Take Jupiter, but crank it up to 10 times its mass. A super Jupiter that's still not quite a brown dwarf. Now park a Neptune-sized moon, like Kepler 1625b, 800 planetary radii out, still safely inside half its hill radius. So far, so good. But here's where it gets wild. That Neptune-sized moon would be perfectly stable way out there. And get this, we could actually give it a massive submoon. Just for fun, let's make it Earth-sized. This whole setup works flawlessly as long as the host moon stays at least 100 planetary radii from the planet, which it definitely does since we placed it way out at 800 radii. So let's summarize what we've got here. A sun-like star with a super Jupiter planet that has a Neptune-sized moon, which in turn has an Earth-sized submoon. Now here's a crazy thought. Could that Earth-like submoon itself have a moon? I'm not even sure what we'd call that. A moon? A sub-submoon? You tell me. Here's how the numbers work out. The Neptunian moon has a hill radius of 276 Neptune radii. If we place our submoon at about 130 radii to be safe, that gives the submoon its own little hill radius of about 135 Earth radii. Plenty of space for a sub-submoon. If we push it to about half that distance for stability, around 60 Earth radii, we could fit a sub-submoon up to about 50 kilometers wide. A nice, respectable asteroid-sized object. So the math suggests, yes, you can absolutely have moons of moons and maybe even moons of moons, though you'd need some very specific conditions to make it work. There is one catch, though. Current calculations account for the submoon's orbit changing over time, but not the host moon's orbit, which isn't realistic since we know moons drift too. This would make a great research project for someone, redoing these calculations to account for both motions. I'd be happy to offer advice if anyone wants to tackle this. Now, if we do find one of these someday, what should we call it? I've been using sub-moon in this discussion, but other suggestions include moon, or maybe moon squared or moon cubed. Another idea might be to drop moon entirely since it gets confusing. After all, we don't call moons sub-planets. These calculations remind us there could be entire classes of astronomical objects still waiting to be discovered out there. This is why astronomy, even as the oldest science, continues to fascinate us. we've barely scratched the surface of what's possible. Submoons, quark stars, cosmic strings, and who knows what else we haven't even imagined yet. I know some people find the unknown frustrating, wishing we lived in a time when everything was already discovered. But personally, I think it's incredible that we get to live in an age of discovery, where there's still so much left to wonder about